So you can take any knot and mess with it. Like you can take the zero knot, or we call this the unknot, sometimes called the trivial knot. So you can take that and twist it, and it looks different, but I can untwist it and it becomes back to the zero knot. There's actually a free software called Knotplot, where you can actually design knots on it and actually see what they look like and let them deform. I have it on mine, but I'm not sure if it's for money at this point. It's not. It's because it's hard to draw these, and if you're a knot theorist, it's difficult. You can see, like, how would I know if I draw something if it's genuinely going to be a something else? I won't be able. If I drew something complicated, I wouldn't be able to see that it's something else. That it could be distangled and be something else. So that's going to take a little while to come up. There it is. Yeah, it doesn't let me use it anymore. But it still might be, you could probably download a free version of it. This was downloaded a while ago. No, it isn't. It's by mathematicians, open shareware. Okay, so the problem with crossing, like if I would look at the crossings alone, is that if I take this unknot and twist it, it puts a crossing there. A crossing is just exactly what you think it is. It's a place where you have a crossing. And so this is kind of like an artificial crossing. And so our definition of a crossing number is when you consider all the diagrams that you could possibly make. So I could take that zero knot and keep twisting it, and it'll have a whole bunch of crossing numbers, different ones. But the minimum number is zero. The zero knot has a zero crossing number. So the crossing number is defined to be the minimum number of all possible distortions of the original knot. So you take, the minimum number of crossings. So you see how, like, this one gets you out of jail? You don't have to know what those crossings look like. It's just the minimum number of those crossings.
What does that say? Consider all regular
diagrams. So all regular diagrams of a knot. So I just showed you two for the unknot, the zero knot, and then twisting it once. So C of K is the crossing number. It's the minimum number of all the crossing points. So the first, the one, if you go back to the other one that I showed you, this one, the crossing is zero. That's the minimum possible for any knot. So this one gave you something larger. So all possible twists and turns of this thing is going to give you larger and larger crossing values, points where they cross. And so you take the minimum number, and the true crossing number is going to be zero. It's really hard to talk about this without talking about equivalence relations, which is something in a traditional class, foundations class, we talk about it at the beginning. We might have talked about it. You know about equivalence classes. You've used them since you were in second grade. When you have a fraction 2/4, it should bother you because 2/4 is really 1/2. So 2/4 and 1/2 are what we say equivalent. And that's supported by some kind of relationship that you learn, kind of like all the other definitions. I'm going to skip over it here. But really, you take all the fractions that are like 1/2, and you put them in a box, and you label the outside of the box 1/2. So you've been working actually all your life with equivalence classes without really knowing what that was. The same thing about knots, or you would take, if you can take one knot and deform it into another knot, we would say that they're equivalent. So if I can untangle it and it becomes the other knot. That's why the knot plot program is really good, because it will show you the untangling. You can't do it for anything. It's kind of hard, but it's super important to be able to do that. This has an application, by the way. You can look up the history, but the history initially was that Lord Kelvin, the Kelvin temperature guy, he thought that the air was knotted. He was wrong, but knot theory became a thing when he said the air was knotted. And then after they found out, no, it's not knotted, he's wrong, it became a pure discipline that only mathematicians worked on because they thought it was fun. And then in the 1950s, after Watson and Crick found the shape of DNA, you have that spiral helix that you see, but actually when you look at genetic information, it's twisted and knotted up, and the shape of that knot actually makes a difference in what it can do. So just one DNA versus another DNA, they might have the same symbols and symbolic expression, but if one is twisted and knotted, then it makes a difference on how it expresses itself. And so you'll see in some bioinformatics programs knot theory being taught at the graduate level because it's important, again, to understand what's going on with so here, equivalence classes, in the case of the genetic information, it actually matters. You can't just say 1/2 is different than 2/4 in that case, because they do different things. But primarily, knot theory as a discipline studied by pure mathematicians. Has no application whatsoever outside of, what they're doing. I went to the knot crossing Wikipedia site, and it's super underdeveloped. So if anyone wants to take that on in this class, we can negotiate your extra credit for that, build it back up. First come, first serve. So if you want to do it, you're committing yourself to doing it. So think about it carefully before you contact me, because then I'll start goading you into getting it done. Wikipedia has its own code that you're supposed to type in, kind of like LaTeX. So it's not trivial to put it up there, but it's like empty. And I'm surprised it's empty, because knot crossing is kind of a big deal. So what is a knot crossing is exactly what you think. Wherever there's a intersection, like here's an intersection that's crossing 1, there's another intersection that's crossing 2, and there's another intersection that's crossing 3. That's exactly, so the crossing number would be 3. The trefoil, I already told you, it's a prime knot. It's decomposed as far as it could be. So as you would think, as by its name, the crossing number for the trefoil is 3. And we call that a knot invariant, because if I know that the crossing number of an arbitrary knot is 3, then it shares that with the trefoil knot. It doesn't necessarily mean it is the trefoil knot, but if it was 5, I would know that it wasn't the trefoil knot. So you have some information. It's kind of like Andrew Wiles was doing. He was counting to be able to say something is or is not true. So it's just in the same way we'd say, okay, if I have a knot, I think it's a trefoil knot. I find out the crossing number is 5, then I know it's not the trefoil knot. So that's how we use an invariant. I'm going to show you a polynomial invariant. Those things are really super cool. I see everybody's face going, uh-oh, she thinks something's cool. It's probably not cool. But it is. It's like it's a mixture of algebra, abstract algebra. Abstract algebra really studies polynomials on top of knots. And so it's a very cool, you already did this actually if you took linear algebra. The Cayley-Hamilton theorem, Cayley's theorem, that if you take the characteristic polynomial and plug in the matrix, what are you supposed to get? Did he cover that yet? Anybody take it already last year? Do you remember anything from it? Like that's the linear algebra is linear algebra, and part of algebra is looking at roots. That's what you did for almost all your life. You were finding roots to things. So what it's saying is the matrix is a root of its characteristic polynomial. That's the algebra side. If I got a chance to teach linear algebra, I'd do it the algebra side. But it's less useful that way, actually, though. That's the problem.